Morning, everyone. Come on in. How are we doing? Questions while we wait? We'll do another example of the Epsilon-Delta business before we move on. Well, why don't we just discuss the Epsilon-Delta definition right now so that we understand the graphical implications of what's happening. So definition, we say the limit as x goes to a of f of x is L if epsilon greater than 0 is given, there exists a delta greater than 0 such that if x minus a is less than delta, then f of x minus L is less than epsilon. And before we consider the graphical meaning of this, let's think about what the original definition of the limit was, right? We said the limit was the behavior of f as x goes to a. Here we're saying it behaves like the number L. Or we had said that if f of x can be made arbitrarily close to L by taking x sufficiently close to a. Now compare with this. F can be made arbitrarily close to L by taking x sufficiently close to a. That's what's happening. Isabel is asking, when doing the epsilon-delta definition, can we factor if the function is a polynomial? Absolutely, right? I mean, that could be useful. Absolutely that. From a graph point of view, and you know, I mean, taking x sufficiently close to a but not equal to a, that's where the bigger than 0. I don't know for new web work. I haven't checked. I'll check today if we have covered. I mean, I suspect the new web work is going to be on limits, and I feel we haven't done enough yet. We might have done enough by the end of today's lecture. We'll see. Graphically, what is happening, if you have an A and we're saying the limit is L, in other words, if you take any point x in here, a distance of delta, to take any x in this interval, in the interval a minus delta to a plus delta, this gets mapped to values close to L. That's what we're saying. Isn't there a web work opened up on trigonometric and logarithms and inverse trig? Correct me if I'm wrong, I thought there was one. If there isn't, yes there is. Thank you. All right. Yeah, so the next one following that is going to be on limits. When we've done enough limits, I'll open one up. Well, right, I mean, and that's exactly the epsilon-delta game. What we're saying here is if I give you an epsilon greater than 0, right, you have no control over the epsilon. But if I give you an epsilon greater than 0, you have to display a delta for which this is true whenever that is. The pre-calculus stuff is going to be on the midterm, absolutely. What do epsilon and delta represent exactly? That's right. I mean, think back to the definition we had before. We would say that the limit of f of x is L if f can be made arbitrarily close, right? If f can be made arbitrarily close to L, so the epsilon is the arbitrarily close here, by taking x sufficiently close to A, but not equal to A. So the epsilon represents the arbitrarily close to L thing, whereas delta is the sufficiently close. If you're close enough to A, your function is going to be as close as you want it to L. And let's use this to prove the first limit law. Let's call it that, the first limit law. If the limit as x goes to A of f of x exists, then the limit of the sum exists. And the limit of the sum is equal to the sum of the limits. Asha is asking if a delta value cannot be found for a given epsilon value. Does that mean the limit doesn't exist? It depends what you mean by cannot be found. Just because you cannot find it doesn't mean it cannot absolutely be found, right? But if you can prove that there is no value of delta, right? If you can show that for some given epsilon greater than 0, there is no such value of delta, then yes, this will prove that the limit does not exist. Let's prove this, right? So you remember this limit law, right? I mean, we stated 10 laws. All of these laws can be proven using the epsilon-delta definition. Let's prove the first one. It's a nice exercise. We're assuming the two limits originally exist. So let's give them names. Let the limit as x goes to A of f of x be L, and the limit as x goes to A of g of x, let's call it some big G. What do we want to prove? We must show what must we show? We want to show that the limit of the sum is the sum of the limits. Now, of course, the sum of the limits here, you understand that to be L plus G. So you want to show that this thing can be made arbitrarily close to L plus G. We must show that epsilon greater than 0 given, there exists a delta greater than 0, such that if x minus a is less than delta, then f of x plus g of x, right, our new function, minus the sum of the limits is less than epsilon. This is what needs to be proven. That is our goal here. Let's prove it. But what's given? We know that this limit is L and this limit is G. What does that mean? Let's translate that into epsilon delta. According to this, there exists, yes, x minus a in absolute value is magnitude, or its absolute value. There exists a delta 1 greater than 0, such that if x minus a is less than delta 1, then f of x minus L is less than epsilon over 2. Right? That's because this limit is L. So if you're given any epsilon, and here what I'm saying is, I'm taking epsilon over 2 as my new epsilon, then there exists a delta 1 such that this is true. Similarly, there exists, because of G, there exists a delta 2 greater than 0, such that if x minus a is less than delta 2, then g of x minus g is less than epsilon over 2. Right? Because of the fact that the limit of g exists and is g. Put everything together. How did we get epsilon over 2? It's a valid question. Why epsilon over 2? You'll see exactly why in a minute. We want to show that this is less than epsilon. So start off with this business. What is that? Let's open up the brackets. This is f of x plus g of x minus L minus g, which is, I'm going to group these together and those together. And now the absolute value of a sum is less than or equal to the sum of the absolute values. So this is less than or equal to f of x minus L plus g of x minus g. This is known as the triangle inequality. this is less than epsilon over 2 if x minus a is less than delta 1. And this is less than epsilon over 2 if x minus a is less than delta 2. So first of all, now you understand why epsilon over 2. And what are we going to do? We're going to take delta to be the minimum of the two deltas, of delta 1 and delta 2. So if x minus a is less than delta, then it's less than delta 1 and also less than delta 2, right? This one is the minimum of the two. It's the smaller of the two. So in this case, if x minus a is less than delta, then this is less than epsilon over 2. And that is less than epsilon over 2, which is epsilon exactly what we wanted to prove. And he's asking how we came up with epsilon over 2. Well, now you see it. If every piece can be made less than epsilon over 2, we get the required epsilon. How are we doing? All the other properties can be proven using this Epsilon-Delta definition. Absolutely. If you were trying to do the same with the sum of 3 functions, you could use epsilon over 3. Can we explain the final answer? I mean, what was our goal here? Our goal was to make everything less than epsilon. So if we were able to make this less than epsilon over 2 and that less than epsilon over 2, we get the sum being less than epsilon. We're good to go. So is epsilon a constant based on the number of functions? Not epsilon, but delta. Delta, right? I mean, you have no control over epsilon. You have control over delta, though. What is the value of delta in this case? Delta is going to be the minimum of delta 1 and delta 2. It's the smallest of the two, right? Smallest of the two deltas, which give us this and this respectively. Sean is suggesting delta is independent and epsilon is dependent. It's actually the opposite. Epsilon is independent. You have no control over epsilon. Epsilon is given to you. You want to find a delta. So delta may depend on epsilon. All right, enough of this. Let's move on. Let's move on to a definition. Let's move on with the definition. We say a function is continuous if you can graph, or if you can draw its graph without lifting the pencil from the paper. example. Y equals x squared is continuous. Look. People are freaking out about the Epsilon-Delta definition. Let's stop that. I understand it's tremendously difficult. And I strongly suspect, I have to talk to the other instructors, but I'm fairly confident that it will not come up on any exam. I'll make an announcement as soon as we have settled that. But yeah, let's not focus on that. I mean, I certainly encourage you to do a few examples. It's a tremendously important concept, but it's way too difficult for us right now. In fact, there's a whole course devoted to essentially that Epsilon-Delta idea. It's called analysis. So you're encouraged to take a course in analysis after you've done calculus 1, 2, possibly 3. If you're interested, analysis is the proof of calculus. So they do everything from scratch using Epsilon-Delta definitions. Well, again, somebody's asking, Epsilon-Delta won't be on the exam. I have to confer with the other instructors. I'm not alone. We're 4. We have to come up with some agreement. I suspect that they will all agree on this, but we'll see. We'll make an announcement at some point. Well, I mean, first of all, the limit laws you have to know, and you can prove, I'll invite you to prove the limit laws, the other limit laws using the Epsilon-Delta definition. Very good. So y equals x squared is continuous because you can graph it without lifting the pencil from the paper. The function 2x plus 1. You know what kind of function that is. It's just a straight line. You can graph it without lifting the pencil from the paper. It's a continuous function. Now, if you don't have the graph, how do you tell if a function is continuous? We have a real definition of continuity at a point. We say f of x is continuous. At x equals a, just at one point, if the limit from the left exists, the limit from the right exists, they are equal In other words, the limit itself exists as x goes to a, and they are equal to f of a. Ali is suggesting any function without asymptotes, but that's not necessarily sufficient. Of course, if a function has an asymptote, a vertical asymptote, immediately you can say that it's not continuous. But there are other cases. We'll investigate, right? I mean, essentially you want this to happen. So you can see where things can go wrong. And, let's take this example. If you fix an a here, values close to a get mapped to values close to 2a plus 1. Right? So limit from the left and limit from the right both exist and are equal to 2a plus 1. Right? It's just a polynomial, so you can plug in. And there it is. So, using the limit laws, think back to those limit laws. And let's ask the question, what functions do we know to be continuous? What functions do we know to be continuous? Well, you know that if p of x is a polynomial, you know that the limit as x goes to a of p of x is p of a. This is limit law number 10. And that's exactly what this is saying. Right? If the limit exists, then that means the limit from the left and limit from the right both exist and are equal to p of a. So conclusion from this, essentially conclusion from limit law number 10, polynomials are continuous at any point a, so continuous on the whole real line. Right? Here we have defined continuity of one point, and of course continuity everywhere means continuous at every single point. So polynomials are continuous. Exponential functions, y equals a to the x, well, you know what the graph looks like. It either looks like this, or it looks like this, but either way, you can graph it without lifting the pencil from the paper. So exponential functions are continuous. Logarithms, well, it's just the mirror image. So if that one was continuous, so is its image, namely the logarithm, which either looks like this or looks like this, depending on what the base is. Logarithms are continuous. Trig functions, you know the graph of sine and cos. You can graph it without lifting the pencil from the paper. Sine is continuous. Same with cosine, because it's just the sine function shifted. Tangent, and so on in their domain. Right? So everywhere except at the vertical asymptotes, you're fine. The horizontal line test is not an issue here, right? This function is not one-to-one, but it's still continuous. And using limit laws, let's throw in the limit laws now. You know the sum, you know the limit of the sum is the sum of the limits. You know the limit of a product is the product of the limits, assuming these limits exist. What does that mean? That means that you can add two continuous functions and you still get a continuous function. You can multiply two continuous functions and you still get a continuous function. You can divide and so on. You can do all of these operations on continuous functions. Roots, sums, products, quotients, compositions. Compositions of continuous functions are continuous. Somebody's asking, isn't tan discontinuous? You're right. You're right. But tangent, let's look at tangent. And so on. You're worried that you've got an issue at pi over 2, right? You cannot graph it without lifting the pencil from the paper. But what is the domain of tangent? Well, negative pi over 2 to pi over 2. Not including pi over 2, right? Because your function is not defined at pi over 2. And then pi over 2 to 3 pi over 2. And so on and so on. So it's actually, here's what happens. Mathematically, if you want to be very precise, you cannot talk about continuity at pi over 2 because your function is not defined there. So that's the end of the discussion. The book, however, treats it slightly differently. Because your function is going to infinity at one of the two sides, we're going to say that we have an infinite discontinuity occurring at pi over 2. This is slightly wrong, but that's the approach the book uses. And you know, this is only a calculus class, so we're going to go with that. But really, the real answer is you can only talk about continuity in the domain. And since pi over 2 is not in the domain, there wouldn't be any talk of continuity there. Let's take an so I mean, let's rewrite the definition of continuity. And understand what can go wrong. Right? What can go wrong here? Either these two limits are not the same. So either they exist and are not the same. They could exist and be different from that. Or one of these could be infinite, maybe both. These are all possibilities, things that can go wrong. Let's take a few examples. consider the function 2x and 3x minus 1. And let's talk about the continuity of this function. So someone's asking, tangent x is not continuous. And according to the book would not consider it to be continuous. That's correct. It would not consider it to be continuous because you cannot graph it without lifting the pencil from the paper. It would not consider it to be continuous on the whole real line. So let's talk about the continuity of this function. First of all, this function is made up of two pieces. Each piece being a polynomial. And from property 10, we understand that polynomials are continuous. So this function is going to be continuous everywhere, except possibly at the point where it switches. So immediately, without doing any work, since both pieces are continuous, since both parts are polynomials, and thus continuous, f is continuous everywhere. Except possibly at x equals 2. Everywhere else, it's immediately continuous. The only place we need to worry about is at x equals 2. So now let's worry about that. What do we need to do? We need to check that this condition is met when x is equal to 2, or when a is equal to 2. So let's check. Let's ask the question, what is the limit as x goes to 2 from the left of the function f? For values less than 2, your function is 2x. Whose limit is? Whose limit is 4. Vanessa is asking, why not worry about x being 1/3? Well, when x is 1/3, we're dealing with the function 2x that you know to be continuous. So no worry. So limit from the left is 4. Let's consider the limit from the right. We're going to discuss the idea of Young discontinuity. Well, actually, we'll probably use this example to introduce that term. For values bigger than 2, what is your function? For values bigger than 2, your function is 3x minus 1. Whose limit is? Limit is 5. People are way ahead of us. Even with the lag, very nice. So you're already done. Limit from the left is not equal to the limit from the right. So your function is not continuous. We don't need to worry about f of 2, but while we're here, why don't we, for completeness, point out that f of 2 is? F of 2 is? Well, now, I mean, we're questioning what function we have to use, but you know what function, right? It's this one. There's no ambiguity here. Here you're not allowed to plug in x equal to 2, but here you are. So when x is 2, this is 5, and there it is. So these two things are not equal, and that's it. Function is not continuous at 2. Why don't we take a moment to graph this and understand what happens? Because, you know, these are just two straight lines. So you know how to graph these, right? This is the line y equals 2x from negative infinity all the way to 2. So going through the origin, stopping at 2, right? And, you know, if you look, limit as x goes to 2 from the left, that's 4, and that's exactly suggesting that, right? I mean, as you go to 2 from the left, you are getting closer and closer to 4. And then from 2 onwards, it's actually 3x minus 1. Which looks like this. Should be probably steeper. Right? Where this is 5. So you see that if you wanted to graph these, you would have to lift your pencil from the paper right here. Not continuous. How are we doing? Let's use this example to give this type of continuity a name. If limit from the left and limit from the right both exist, are finite, but limit from the left is not equal to the limit from the right, as in this case, right, as in this case, well, to graph this, you would have to jump from one point to the other. So we call this, we say f has a jump discontinuity. At x equals a. Function is not continuous there. We have a jump discontinuity. Because in the graph, you have to jump from one point to the other. Let's do a few examples from the book. We'll see other kinds of discontinuities and we'll address them when we get there. Consider this. question is asking us to discuss the continuity of this function. So what can we say about the continuity of this function? This function here, you recognize as a rational function, right? It's one polynomial divided by the other. And from your work on limits, you know that the limit is going to exist everywhere the denominator is not zero. So this function is continuous. 1 over x plus 2 is continuous, right? Because it's one polynomial divided by another. It's continuous everywhere except possibly, well, this is continuous everywhere except at x equals -2, right? Everywhere as long as the denominator is not zero. So this function, so f of x is continuous everywhere except possibly at x equals -2. -2, so I mean, you know, this is the last time I'm going to write this down. But -2 is the only place you need to worry about continuity. So let's worry about that now. What is happening at -2? Take the limit as x goes to -2 from the left. What is the function for values less than -2? Well, as long as you're not at -2, the function is this. It's 1 over x plus 2. What is the limit? Right? If you plug in -2, you get a 1 over 0. And you know that in the context of limits, this is some sort of infinity. We have to determine if it's negative or positive. A number less than -2 plus 2 is going to be negative. So the whole thing is negative. Negative infinity is the answer here. And you're done. Immediately, the function cannot be continuous. The function cannot be continuous at -2. And as soon as either a limit from the left or a limit from the right is equal to some sort of infinity, if one of the limits is some sort of infinity, we say f has an infinite discontinuity. Continuity at that point. All right. So here, function is continuous everywhere except at -2, and at -2 we have an infinite discontinuity. consider this example. And let's talk about continuity of this function. Matthew is asking if there's notation for this, or we just write it down. I'm not sure what you're talking about. The limit being negative infinity here, you mean? If we just plug in, you know that we're looking at a 1 over 0. And in the context of limits, this is some sort of infinity. We have to decide the continuous part. So we're saying here that this function is continuous everywhere except at -2. You can write that down. Function is continuous everywhere except at -2. And at -2, you have an infinite discontinuity. Consider this, and let's talk about the continuity of this function. Function is not continuous. So let me make it clear here. F is continuous everywhere except at -2, where it's F, not the point, right? It's not the point that has an infinite discontinuity, but the function itself, except at -2, where f of x has an infinite discontinuity. Or as somebody has suggested, it's really an asymptote, right, Michael? Michael's suggesting that at -2, you have a vertical asymptote. Yeah, so an infinite discontinuity is really the same as a vertical asymptote. Consider this, and let's ask ourselves, what can we say about the continuity of the function? Well, the function is essentially this function everywhere except at 1. So this function is a quotient of polynomials. It's a rational function. So immediately, this is going to be continuous everywhere the denominator is not 0. F is continuous everywhere except possibly at plus or minus 1. Everywhere except where the denominator is 0, you've got continuity. So now we would have to test at plus or minus 1. Let's see what happens at 1. So let's ask the question, is f continuous at 1? So what is happening at 1? We're going to look at the limit as x goes to 1 from the left of your function. And for values less than 1, what is the function? The function is x squared minus x over x squared minus 1. Ali is asking why we write except possibly. Well, I mean, we have to test. We have to test for continuity at these points. Everywhere else, we're good to go. All right. So let's work out this limit. Let's see what happens. And you know, if you blindly plug in, because these are just polynomials, numerator 1 minus 1 is 0, denominator 1 minus 1 is 0. So you have a 0 over 0, which you know to be an indeterminate form. Something's got to be done. What are we going to do here? Factor, very nice. Thank you, Michael. Let's factor. Let's factor out an x from the numerator. And let's factor this as x minus 1, x plus 1. And you see that the x minus 1s cancel out nicely, leaving us with a limit of x over x plus 1, which is easily seen to be one half. And if you do the limit from the right, well, I mean, it's exactly the same, right? It's the same function on the left or the right. So you could have done it just in one step and just have said the limit as x goes to 1. That would have been fine. You know, you don't have to split it up into two pieces when you know what's happening. Here it was the same function on both the left and the right. So you could have done it in one step. We didn't, but there it is. Limit from the left and limit from the right are equal, and they are 1/2. Is your function continuous? We have limit as x goes to 1 from the left. We back? We're good? Still buffering? We're back, thank you. Excellent. So we need the limit from the left and limit from the right to be equal, but we also need it to be equal to f of 1 in this case. And f of 1 is equal to 1. So they're not equal. So function is not continuous. Let's understand what would happen. What would the graph look like? For values close to 1, your function is close to 1/2. But at 1, your function is 1. So you see why it's not continuous, right? There's this hole here. The idea being that if you were to redefine your function just at one point, you could make it continuous, right? So by changing your function just at this one point, your new function would be continuous. This is known as a removable discontinuity. You can remove the discontinuity by just redefining the function at one single point. Guillaume doesn't understand f of 1 equals 1. I mean, we have no say in the matter. When x is 1, your function is 1. It's given in the problem. Exactly that. Matthew, how come it's plus or minus 1? I don't know what you're talking about. Are you saying 1 from the left and 1 from the right? Oh, you mean here, perhaps. Well, I mean, if the denominator is plus or minus 1, you're dividing by 0, so you've got an issue here. But yeah. So what are we saying? Your function is not continuous at 1. At 1, you have a removable discontinuity. What about at negative 1? What is happening at negative 1? For values less than negative 1, your function is this. Absolutely, right? I mean, there's still an issue with the minus 1. We have to test that as well. And what happens here? If you plug in negative 1, this is 1 minus negative 1, so 1 plus 1 is 2, over 1 minus 1, which is 0. So you've got a 2 over 0 here. You've got a 2 over 0, which you know in the context of limits is some sort of infinity. You now have to determine if it's positive infinity or negative infinity. And the answer here, numerator is close to 2, so that's going to be positive. A number less than 1, when you square it, you get something bigger than 1. Something bigger than 1 minus 1 is going to be positive, so positive on top, positive on the bottom. You have a positive infinity, and there's no need for you to go further, i.e. infinite discontinuity. At negative 1. So Ella is suggesting a removable discontinuity just means that there's one point that doesn't work exactly that. Why is it positive infinity? Well, you tell me. If you take a number less than negative 1 and you square it, I claim you get something bigger than 1. Minus 1 is positive, and 1 minus negative 1, or 1 plus 1 is 2. Numerator is positive, denominator is positive as well. Can we go over the graph? Can we go over the graph? Well, from this work here, your function is essentially x over x plus 1, whatever that graph looks like. I don't know offhand what that graph looks like. We would have to do some work, and we're going to do that in this class, just not right now. But maybe in about a month, we can graph this together. All right, let's move on. You're talking about the one I drew right here? Right here, I'm suggesting the limit from the left and limit from the right are both 1/2. So close to 1, your function behaves like 1/2. Except at 1, your function is 1, right? So, I mean, it's a terrible graph, but it's the idea that's important, right? For values close to 1, you're going to be close to 1/2. But exactly at 1, you're at 1. So you still have this hole happening here. The function is not continuous. But if you think of removing this point, just one single point, and redefining it there, Now everything is nice and continuous. So if you were able to redefine your function just at one point, your function would be continuous. We call this a removable discontinuity. Let's consider this question. Now that we have understood continuity, we can use continuity to help us evaluate limits. How so? Well, you know that sine is continuous. So what does that mean? That means that limit as x goes to a of sine x is going to be sine of a, which can be thought of as sine of the limit. In other words, you can bring the limit inside. So we can bring the limit inside. We can bring the limit inside. So this is going to be sine of the limit because sine is continuous everywhere. And now we can do the same thing because tangent is continuous everywhere except at odd multiples of pi over 2. Why can we bring the limit inside? Exactly because of continuity, right? Limit as x goes to a of sine x is sine a, which can be thought of as sine of the limit. So it's exactly because of continuity that you can bring the limit in. And you cannot bring it in otherwise. And similarly, tangent is continuous everywhere except at odd multiples of pi over 2. So as long as this is not going to be an odd multiple of pi over 2, we're good to go. But looking ahead, cosine, the limit of the cosine, as theta goes to pi over 2, is going to be cosine of pi over 2. So here the ends justify the means. And because the limit of cosine is not an odd multiple of pi over 2, you're allowed to do this. And now you know what that is. This is just cosine of pi over 2. Again, because cosine is, so this is because since tangent is continuous, except at odd multiples of pi over 2, and this is not an odd multiple of pi over 2 because you're working ahead, and this is actually cosine of pi over 2 since cos is continuous. And cosine of pi over 2 is 0. And tangent of 0 is 0. And sine of 0 is 0. And there is your answer. Kamal is asking, isn't pi over 2 an odd multiple of pi over 2? Yes, it is. But it's cosine of pi over 2. that we're interested in. Is cosine of pi over 2 an odd multiple of pi over 2? And it is not. Let's try another. Can we go over why it became this? Well, cosine of pi over 2 is 0. And that's it. So is tan considered a function with a removable discontinuity? No. No. Tan is a function with infinite discontinuities at odd multiples of pi over 2. All I'm saying is continuity is what allows you to bring the limit inside, right? Continuity, by continuity of sign, you know that this limit is that, which can be viewed as this. So it's like just taking the limit of the x. That's what continuity allows you to do. Consider this. We have an exponential function. You know the exponential function is continuous everywhere. So limit of the exponential function is 3 to the limit. Because 3 to the x is continuous. And now, limit of the square root is the square root of the limits. Right? In fact, that's one of the properties. I want to say property 5. Could be wrong here. And now, it's really due to the fact that the square root function is continuous. So this property 5, or whatever it is really making use of the fact that the root function or the power function is a continuous function. And now it's the limit of a polynomial, which by property 10 is just a polynomial. So I went from 4 to A there, sorry. So limit laws only apply to continuous functions? No. No. But limit laws can be redefined in terms of continuous functions. They can be reapplied to continuous functions. And yeah, that's it. Right? I mean, you want to be careful with the root-ish. Yeah. So, I mean, in some cases you want to be careful, but yeah, no, Michelle is correct. There's no left-handed limit. You could, and the book does redefine continuity in terms of just one left-handed limit or just one right-handed limit when the function doesn't exist on the other side. I didn't want to discuss that, but yeah. What do we have here? By property 10, this limit you can just plug in, which is again the continuity property of polynomials. So if you plug in 16 minus 8 is 8, minus 4 is 4, square root of 4 is 2. This is 3 squared, which is 9. Very nice. Now, of course, in the same way, when you're taking limits, you don't always refer back to all the limit laws. We're not going to do that here either, but understand that everything can be justified, in this case, using continuity of a few functions. Why do we only take the positive square root? Should we have plus or minus? But nothing is mentioned here. So it's understood to be the positive square root. Monica is asking how continuity relates to this question. Well, it's continuity that allows you to just take the limit of the power. Ali, I think I just answered that. Nothing is mentioned in front of the square root, so it's understood to be the positive square root. Show that this function is continuous on all of R. Immediately, you know that sine and cosine are already continuous functions. So the only place we need to worry about, f is where the function goes from one to the other, namely at pi over 4. So f of x is continuous everywhere, except possibly at pi over 4. Is that clear, everyone? I assume it's very clear that pi over 4 is the only place we need to worry about, because it's the place where you go from one function to the other. The real question is, on a graph, is that going to be smooth? Is it going to be a smooth transition or not? That's really the question we're asking. Now, so we're going to test for continuity of pi over 4. What do we need to do? We need to look at the limit as x goes to pi over 4 from the left. And what is your function for values less than pi over 4? For values less than pi over 4, your function is sine x. And what is this limit? You know that sine is continuous. So limit from the left is limit from the right is sine of pi over 4, which is 1 over root 2. And similarly, limit as x goes to pi over 4 from the right, what is the function for values bigger than pi over 4? For values bigger than pi over 4, your function is cosine. And once again, you know cosine to be continuous. So limit of cosine is just going to be cosine of pi over 4, which is 1 over root 2 again. So right away, you have limit from the left equals limit from the right. That is not enough to guarantee continuity. You also need to check what happens at pi over 4. And what is f of pi over 4? Where do we plug pi over 4 in? First function or second? You know what it is. It's exactly at the second, right? That's the only place you're allowed to plug in pi over 4. This is cosine of pi over 4, which is again 1 over root 2. Exactly, thank you. So now this is equal to this is equal to this. They're all equal. So we have continuity. At pi over 4, but we already had continuity everywhere else. So continuous on all of R. Convinced? How you doing? Questions? Are we good with this? Shall we do one more? Let's do one more. Or two. One or two more. Certainly better than Epsilon-Delta for sure. Yeah. I still haven't posted any office hours. I'll do that over the weekend. But if you need to see me in the meantime, email me. All the other instructors and TAs have office hours. So you're certainly welcome to go talk to them. But if you want to talk to me, just email me. We'll set something up. Or just oftentimes a few email exchanges does the trick as well. All right, consider this. We're asked to discuss the continuity of this function. And what can we say? This function is made up of 3 pieces, all of which are continuous. 2 to the x is continuous everywhere. Three minus x is continuous everywhere. And square root of x is continuous on the interval 0 to infinity. Right? You know what the graph looks like. This is just a straight line, and that's the exponential function. So these 3 pieces are themselves continuous. Notice that the square root here is only for values bigger than 4, which is contained in here. So there's no messy business happening here. There's no need to worry about negative values of x. So this function is made up of 3 pieces, all of which are already continuous in their respective domain. So the only place we need to worry about continuity is where we're jumping from one to the other. This function is continuous everywhere. Everywhere except possibly at the points where they go from one to the other. In other words, x equals 1 or 4. 1 and 4 are the only places we need to worry about discontinuities. So let's see what happens there. By looking at the limit as x goes to 1 from the left, what is your function for values less than 1? When x is less than 1, the function is 2 to the x. And what is this limit? This limit is just 2 to the 1, which is 2. Right? By continuity of the exponential function. What about limit as x goes to 1 from the right? What is your function for values bigger than 1? Well, now, some of you might think there's an issue. When x is bigger than 1, which function do we use? Don't we have to consider both? Shouldn't we consider both? The answer is no. We only need to consider one of them, namely this one right here, right? Because we want here the limit is the behavior as x goes to 1 from the right. We're looking for the behavior of the function for values very close to 1. Here, this function is not close to 1. This is for values bigger than 4. 4 is not close to 1. We have to use 3 minus x. Whose limit is? Tina gave it to us a while back. Whose limit is 2? So these two agree. We have a third condition for continuity, f of 1. And what is f of 1? Again, 1, you're only allowed to plug it into this. It's 2 to the 1, which is 2. So now you see this, they're all equal, i.e. continuous, at x equals 1. At 4, what is your function for values less than 4? For values less than 4, again, you have to use a function 3 minus x, right? Not the function 2 to the x. That's way too far from 4. This is the function for values close to 4, but less. And the limit here, -1. Limit as x goes to 4 from the right. For values bigger than 4, you know what function we're dealing with. Root x, whose limit is 2. So you see that these two limits are not equal. For For completeness, although you don't need to mention it here, but what is f of 4? You tell me. F of 4 is? Anybody? -1, thank you. F of 4 is -1, right? You're only allowed to plug in 4 into this function to get -1. But now, again, right, this was not necessary to answer the question here. These two things are not equal. So we have a discontinuity here. What kind of discontinuity? Yeah, Sean, that's exactly my question to you. What kind of discontinuity? A jump, thank you. Jump discontinuity at x equals 4. Very nice. There it is. So, a good place to end. You guys do some exercises on this continuity business, and we'll pick this up again on Monday. Thank you all for coming. Not removable, Ali, but rather jump. Removable is when these two are equal, but not equal to this. What does a jump discontinuity mean? If you were to look at the graph, as you approach 4, here, from values less than 4, we're going to -1. But from values bigger than 4, we're close to 2. So you're jumping from one to the other. Here it's actually a, right? So your function will look something like this. Very good. So practice this, and we'll pick this up again on Monday. You guys have a good weekend. I'll see you then.